طيب, Bismillah ar-Rahman ar-Rahim. So we started to talking about datagram forwarding. Of course, we talked about virtual circuit, and we said that virtual circuit is outdated. So the internet is by far dominant by IP. And IP uses datagram, and that's mainly for scalability issues. So virtual circuits, we have to deal with millions and nowadays billions of circuits, and that's not scalable. So IP or the network should be very simple to support scalability. And then we push the complexity towards the edge. That's why TCP has to handle flow control, congestion control, reliability, and so on and so forth. And this happens at the edge, right? But the core network should be simple so that we can enhance the scalability. So with that, we talked about datagram forwarding. And we said that we have the routing table, which maintains all the destination addresses. But the problem is, potentially, we have 4 billion IP addresses. So where does that come from? Why 4 billion?
4 billion devices.
4
billion devices.
Not necessarily. No, we have more than 4 billion devices. We have potentially 30, 40 billion devices.
But we are talking about at one time. At the same time, we have this maximum.
No.
The IP address range, I guess.
أيوة, low A. IP address, how many bits? How many bits?
V4 or V6?
How many bits IP address?
8 by 8 by 8 by 8.
لما كام يعني? 32, okay. How much range does that give us?
We don't use all the ranges actually.
لا, we do, in a way يعني.
Like so many with that.
2 to the power 32. هي 2 to the power 32 is 4 billion addresses. You can calculate it يعني. فهي 4 billion addresses. بس هل 4 billion addresses are enough? Even 4 billions are not enough.
This is the V4, right?
But we have
V4.
Yes, V4. طبعا for V6 2 to the power 128. That's another story. We'll talk about this at some point. But يعني at least for IP version 4, we have 2 to the power 32, which is like 4 billion devices. Even that is not enough, and we know that, and that's why we have other like other ranges of IPs which we can be reused. That's another story. But we have some other mitigation techniques to make it even more than 4 billion devices. But can you imagine that you have 4 billion rows in one routing table in every router on the internet, which means that every router on the internet can route from any point to any point, from any IP address to any IP? Of course, that's not possible, صح? 4 billion rows in one routing table is not feasible, right? So we cannot have this. So that's why the routing table is not per single IP address. So we have ranges of IP address. Okay, and range of IP address usually refer to a full network. So we want to route data from one country to another country. Okay, so we care about routing this data from one country to another country. This country has range of IP address. I don't care, because within this range of IP address, I will use another level of layers, which is the data link layer, to really deliver the message to a physical device inside this country. Okay? That's another level. But as far as routing is concerned, I need to move it from Qatar to China. But within China, I will use physical address to deliver this to a particular person in China. Or يعني مثلا I will use مثلا IP address to deliver it to a specific house. And then inside this house, I will use the physical address, which is my name. I need to deliver it to Amr, so I use the physical address of Amr. And that physical delivery happens in the data link layer, using wireless, using Ethernet, using something else. But for routing, I need to deliver it from one location to another location. Within that location, definitely I will have hundreds or potentially thousands of devices.
So we handle some of the responsibility to other routers.
Right, and that's also to make it, again, to make it simple so that we make it scalable. So instead of having 4 billion rows in each routing table, now I will have few number of rows. Okay? So I will have only one range of IP address. So one entry here refers to a full location, which might be a country or a big city. Okay? So this way I can reduce the size of the routing table. So this is the first level that we need. So aggregate table. That's an example. So I can, طبعا addresses, they can be translated eventually in binary. And each of these correspond to a byte that can be converted to a dotted decimal notation. So each of these bytes can be converted to decimal, and then we convert that to a dotted decimal notation. So for us, that's a range. And as you can see here, this range is actually common until here. So the part on the left-hand side is common between these two. And these bits, they change from all zeros to all ones. I don't care, so I need to, so the location will be referred to by what we call this is the network address. This is what we refer to in network 1 as the network address. The network address refers to a full network, which might refer to like a country or a city or a big location. Inside this location, I don't care which device this message should be delivered to, because this will be the responsibility of a data link layer using the physical address to transfer this or to deliver this to a particular device. Okay? So that's how I specify a range. So I specify a range in the routing table based on this common part. So this common part will be the part that I put inside the routing table. So each one line will refer to a big, huge location. Okay? And as you can see, I need to deliver this through a specific output port. So the router actually, from a hardware perspective, it's actually it has multiple ports. Each port could be an input port or can be an output port. So I need to deliver it from port 0 to port 3, for example. Okay? So regardless of where it's coming from, I need to deliver this to port 3 or port 2 or port 1 or port 0 and so on. Each one of these refers to a specific next hub, which could be, one could be in Emirat, one could be in China, one could be in anything, okay? Of course, there is what we call otherwise. Otherwise here refers to this is also another trick that we use to really reduce the size of the routing table drastically. We have what we refer to as a default, this is what we refer to as default route. Default route معناه if I don't have any match between these, by default I will send it through this output port. This output port will be connected with another router that will possibly route it correctly. But for me, this is my default route. Okay? So if I don't have the packet that is coming in will have the destination address. If the destination address does not match any of these rows, then I will send it through the default route. We'll see how this happens now.
How can I make sure that the devices in this particular location will be falling into the same range of IPs?
It must be. It must be. طبعا it must be. If it's not, by the way, you have a network error على طول. You have a network error. Yeah, for example, once you open Windows, Windows, I don't have to get to these details, but Windows will have to negotiate the IP address with the DHCP, which is running on the router. So the DHCP server will give it an IP address. If you use an IP address which is not in this range, the Windows will detect it and will give you an error right away.
Give you another.
طبعا. Will give you an error.
That's all.
So yes, so Windows will have to negotiate this IP address with the DHCP server, and will have to give you an IP address in this range. Okay. طيب. But what happens now if ranges don't divide up so nicely? That's what we referred to طبعا, because we have يعني برضو we studied that in network. We have classless, classful, and so on. So usually these ranges, they do not have to be equal. They do not have to have equal number of addresses in each of these entries. Okay, so that's why we in network one we studied what we refer to as subnet mask. Subnet mask. Okay, so these ranges, they do not have to be equal. They do not have to be homogeneous. Okay, so for example, if I see a routing table that looks like this, طبعا احنا the way that we represent each row is by putting what we call the network address. The network address is the part that is common in all this range. Okay? This means that this part could be different, could range from all zeros to all ones and have any combination. I don't care. Okay? So if I have a network address that looks like this means that this network or this location in general can support up to how many devices? 2 to the power 11, bravo Ali. 2 to the power 11, that includes all by the network address and broadcast address and everything. صح. This is 2 to the power 11. How many here? Huh? 2 to the power 8. Are they equal? No, this one is a location that must have more devices than this one. They do not have to be equal. Okay? So that's in a way good, because otherwise I will have to assume that all locations will have the same number of devices. And that's not practical, because here in this meeting room, you cannot assume that you have the same number of devices in this meeting room like another lab which can have only مثلا 20 مثلا locations. This will have, let's say, I don't know, 40. Another lab will have 100. Okay? So locations are by default different in terms of how many devices it may support. تفضل.
I have a question about the routing table.
Mm-hmm.
You said they share the network address, but how many routing tables are there usually? Like, does it depend on
Every single router should have a separate routing table.
every single router?
Yes. And
But one router cannot have more than one routing table, right?
usually no. Usually it has one routing table and other supporting tables, which we don't have to get to. So other complementary tables, but they are not routing tables. Okay, we don't want to get to this.
So we decided the subnet already.
Yes. So this table, by the way, it gets negotiated between the routers. Each router, when it first starts, it should get information from all the Ethernet and all the LANs that it's connected to. Okay? And then it sort of plans all the ranges of IP address for all the ports, and each port is connected through wireless or wired or something like this. So when I first start, the router would have information immediately about all the LANs that it's directly connected to. Okay? But the router in Qatar does not know anything about the router in China initially. صح? So they will start to iteratively negotiate and exchange information about, I have these LANs with these ranges of IP address. So the other router will say, I have these LANs with this range of IP address. Okay, so I know now that if I want to send something through to مثلا China, I need to send it through Al-Emirat مثلا. Through this negotiation of information or exchange of information. Again, we don't have to get to these details now. This should have been studied in other courses, and there is no time to study this now. But what we're trying to stress now is that there are some tips that we can use to reduce the size of the routing table and make it fast and scalable. One of them is the ranges, but these ranges are not necessarily equal. Okay, and they should not be restricted to be equal, because this will mean that these addresses are not assigned proportionally to the number of devices in that location, which by default are different. So we should not restrict these ranges to be equal. The other thing is what we refer to as the default route. So this is like the default route. So if I don't have a specific match about these ports, by default I will send it to the fourth port, which is connected to another router. Hopefully when it goes to this router will do the same process and will do this iteratively until it gets delivered, hopefully, to the final destination. Okay? Type. So when looking for a forwarding table entry for given destination address, use the longest. This is a very, very important rule. Because the logic that we use here is that the router receives a packet, صح? The packet has IP header, صح? All we care about in this IP header is a field called a destination address. That's the only thing we care about when it comes to consulting the routing table. So we get this destination address, and then we try to find a match between this destination address and any of these rows. Okay? So what is the rule now? This destination address, remember, we match a full address. خد بالك, the packet is coming with the full address that includes the IP address of a particular host. Okay? The IP address of a particular host will not have stars like this. Will be a full destination address that refers to a particular host. Right? Okay. That would potentially mean that this destination address will have partial match with some of these entries. So if I line up the destination address, so this is example number one. The incoming packet would have a destination address that has this full IP address. Okay? So let's see how we match. We match this with each of these entries. Okay? So this address matches with which row here?
First and second.
لا, second is first. صح. First, صح. طيب, second, does it match with the second one? No. No. 1 0. لا. Only the first one. صح? That's good news. There is no ambiguity here. صح? Okay, خلاص. So this will have to be sent to interface A. Okay, that's good. Let's look at example number 2. Example number 2 here matches with what بقى? Second, and خد بالك, what if it does not match 1, 2, or 3? It goes to a port 3. That's fine. So default route is always there. This matches with anything. Okay? But why did we say port 0 and not port 3 for number 1? Because this otherwise matches with everything, صح? Why did we say this? Because of this rule. If it matches with this and this, okay, then we take the one that has the longest match. The longest match. This matches with /0, which means that if it matches with this, معناها there is no other match. Okay? This one matches with how many bits? 8 plus 8 plus 5. 21. So we have 21 bits that match. And that's the longest one. Okay? So خلاص, we take this longest one. Number 2 here, this destination address matches with 2 and 3. For 2, for this entry 2, it matches with how many bits? 24 bits until here. صح? For this row 3, it matches with how many? So this one matches with 24 and matches with 21. Which one will we select? 24. So this will have to go to a interface number 1. صح? 1. So this one will be output to interface 1. Output interface number 1. واضح كده? Anything not clear? So this rule is very important. So this way we can preserve the fact that we have unequal ranges, okay? And if we have multiple match, we get the longest match and then we send it through that output port. واضحة كده؟ So that's a two ambiguity. Sometimes you have like 3 or 4 matches. So you select the one that gives you the longest match, which means that potentially if you have an entry that refers to one IP address, one full IP address, and you have full match with all the 32 bits, خلاص, this is the best. Send it to that particular host. Because sometimes you have a host that's directly connected to a router through a point-to-point. There is no Ethernet, there is no wireless, there is nothing. Point-to-point. Host connected directly to the router. So in that case, you will have an entry that refers to the full host IP address in the routing table. So you will deliver it directly to that host. So if you have a match, an exact match with all the 32 bits, you deliver it directly to that host. مفهوم كده؟
But this is not the case usually, right?
Why? In your house مثلا.
The router in the house is
Yes.
Ethernet.
Yes. It has direct connection point to point with some wired devices.
Yes, correct.
Okay?
We go through the entire routing table every time we have a destination.
Yeah, that's a good question. That's why we have binary. Sometimes this matching process is done through hardware. Yes. So why do we have this longest match? Because we do it using registers. So in hardware, this would be done very fast. Okay, but you're right. Yes, we have to match it with all the entries, and practically you might have tens of matches. So you have to select the longest one. Yes, that's why this forwarding process, it's still until today, despite all the software-defined networks and all the things that we talked about last time, this is done in hardware inside the router. This is the process that we do. The control part can be pushed to software, can be done in the cloud, but the forwarding part has to be done through hardware. It has to be very fast. Okay? So this is a summary of what we discussed so far. So we have the internet or datagram and we have the virtual circuit. As we said, this part is a little bit outdated and it's kind of obsolete now. So the internet is predominant now using the datagram and IP. So IP is the only, you can say IP confidently, IP is the only network layer protocol currently dominating the internet. So as we said, we try to reduce the complexity of IP by making it best effort. We don't have to provide any guarantees because providing guarantees requires that you need to establish virtual circuits, and virtual circuits are not really scalable. So we have to make it elastic. Elastic here معناها best effort. So there's no guarantees, no strict deadlines. There is nothing, and we have to do it this way to preserve the scalability. And we pushed, as we said, we pushed the complexity towards the edge. So the end systems, referring to as the edge, are now complex. So we have to do flow control, congestion control, and so on and so forth. Provide strict guarantees in the TCP level, not in the network level. Also here we deal with many link types. We have to deal with, this is a very important characteristic now, that IP in the network layer, we always refer to the next hop that potentially uses different technology. So you might be dealing with Ethernet, you might be dealing with point-to-point, you might be dealing with wireless, you might be dealing with satellites. Okay, so from one hub to from one router to another, you may be dealing with a totally different technology. But you might say that, why does the router have to care about the next network and how it looks like, whether it's Ethernet or wireless or satellite? It shouldn't, right? Because as we said, layers are supposed to be isolated, صح? So why does it matter to say that the next hop is really wireless, or the next hop is Ethernet, or the next hop is satellite? Okay, there is only one implication that IP had to deal with, especially in IP version 4, which we will talk about today. And even that implication has been removed in IP version 6. We'll talk about it later. Okay, but let's now focus on the difference. So here in virtual circuits now, it's evolved from telephony. Telephony really was based, as we explained before, was based completely on establishing physical circuits. That's why we say it's evolved from telephony. So in the network layer, we're talking about not a physical circuit, but we're talking about logical circuits. We call it a virtual circuits. Okay? It's not necessarily physical, but it's a logical circuits. So it's strict timing, reliability, and requirements. So we can actually provide pair circuit behavior. If we have millions of these virtual circuits established end-to-end, the router has to maintain a state inside the router for all these virtual circuits that passes through this router. So the router at least has the capability, theoretically, to provide pair circuit behavior. So I can select one circuit and give it more buffer size, give it more bandwidth. I can do that because I maintain a separate state for each virtual circuit. But IP doesn't do this. It cannot do this, okay? In that case, the end systems are dumb. Sorry for the word, but it's dumb in the sense that telephones in the past, they were dumb. They used one thing, encoding, decoding for the voice. That's it. They don't have to provide any network function at all. They don't have to provide flow control, congestion control, establishing connection. They don't have to do this. Okay? But in datagram, TCP does most of the work actually. Okay? واضح كده؟ That's the difference. So now we will switch to a 2.3, another topic now. So we need to take a deep dive inside the router. Okay? From an architecture point of view, we need to look inside the router and see how the router is designed in hardware. Okay? So this is a crash computer architecture part. Okay? So we'll have to look at how the router is designed from inside. So this is the high-level architecture of the router. So the high-level architecture inside the router is actually divided into physical ports. صح? We know that each of the ports connected to the router can be an input port or an output port at the same time. صح? But when we look at it from an architecture point of view, we say that there is some input ports and there are some output ports, which means that input ports is where the packet comes from, and output ports are where we should send the packet next. Each input port has 3 boxes which refer to the 3 layers. Okay? So the first thing is a physical layer. And this is the data link layer, and this is the network layer. So each of these boxes refer to the actual layers. So what I receive here on this input box is actually, or input port, is actually signal, physical signal. It's an analog signal or a digital signal. Okay? So I need to do what? I need to do channel estimation, possibly sensing the line to see the energy level and so on and so forth. That's what this box does. Okay? The physical one. Okay? And then we get to the data link layer where we have to convert the bits into to frame. So here we have to do framing. So we have to divide the bits into frames. Okay? And then we have to do like some error control. Do we have any error in this frame? Because if we have any error, خلاص, I'll need to drop everything. خلاص, I don't need to do anything. Okay? So we do the framing. Sometimes we do برضو some level of flow control here. Okay? And then we send it to the input port. The input port for us is a buffer. This is where we have to store these packets into a buffer. So we convert it from a frame to a packet, and in the packets we have to store it into a queue, a buffer which is represented by a queue.
So
Okay? So from here to here, we have to do decapsulation. Remember we talked about encapsulation and decapsulation? So we have some bits. Bits get converted to a frame. The frame is data and a header. So we go from here to here, we extract the header, throw it away, and then we send it to the network layer. The network layer is a packet. The packet has the IP header and the TCP or UDP payload. We store this into a queue. واضح كده؟ So until here, we have set of packets in a queue, sitting in a queue. Okay? Why do we have a queue? In any systems, by the way, if you have input process and output process which could have different speeds, then you have to queue things. يعني بمعنى, we are all going to a bank to receive a particular service. Okay? Can we assume that everybody gets into the bank, they will have an instantaneous service from a teller or from a customer service so that we have only one customer at a time inside the bank? We cannot do this. So we have to have a queue. Okay? So the queuing system is used whenever the input process and the output process, they could have different speeds. Okay? And that's particularly the case here. We have incoming data which might come with a particular rate that we do not expect. But the service rate here is based on some factors inside the router, and we have almost more or less a particular service rate. So the router takes a specific time to process one request. So here, the service rate has a limit. Okay? But the incoming traffic, we cannot expect. So we should have a queue. Okay? A queue is a first input, first output. Most of the routers, they use the queue system. Some of the routers, they use different complicated queuing system. We'll talk about some of this, but we don't have to get into the details. But we understand now why do we have queue in every input port, and in fact, in every output port, same thing. We'll talk about the output port. So in terms of an architecture, we have input ports, and each of these boxes correspond to the particular layers, and we have what we call a switch fabric. A switch fabric, this is a physical architecture. We will get into the inside parts of this to see how we can, in hardware, as I said before, this process has to be extremely fast. That's why we do it in hardware. Okay? Which allows us to have all the degrees of freedom to send the packets from any input port to any output port. So we need to have a specific design here in hardware, okay, that allows us to very fast deliver one input packet from one input port to any of these output ports, depending on what? Depending on the destination address in this packet, which gets matched with the routing process or the routing table. So that's why there is a control part or there is a routing processor. This part can be done partially in software. So there is, again, the forwarding part and there is the planning part. We said that there is a difference between establishing end-to-end route and doing the forwarding part. Doing the forwarding part is mostly hardware. Planning the end-to-end is done usually in software, which we will study later in this chapter. Okay, that has to use lower routing algorithms, which plan the route of the packet end-to-end from Qatar all the way to China. Okay, this part can be done in software, and usually it requires what? It requires some entity with high-level picture that looks at the entire map of the world, right? Like Google Map. Okay, that's why this part is a control part that can be pushed to the cloud in some cases, like software-defined networks. But the forwarding part still maintained in hardware, which is done inside the router. Okay? تمام. So these are the layers, as we said. We have the physical layer, which is the lowest layer. It receives an analog signal or a digital signal, depending on whether you are using baseband or broadband or wireless or something like this. And then it converts, it does a channel estimation and converts everything into bits. From bits, it goes to the data link layer, which then handles if there is a collision, if there is sensing on the channel, carrier sensing for the case of wireless, things like that. Okay? And then it goes to the queuing system. The decentralized switching here, given datagram destination, look up output port using forwarding table in the input memory. So the goal here is that complete input port processing at line speed. So so remember here, this is a very important goal here. Potentially, I need a very fast forwarding process which allows me to potentially switch packets on all the input ports. Even the worst case scenario, what is the worst case scenario inside a bank? I have 5 doors, okay, representing the different input doors to the bank. All of them are going to the teller, okay? If I want to maintain a specific output speed from the teller, what is the worst case? The service rate from that teller should match n times the speed of the incoming packets on all these ports. صح? صح? So in order to maintain, if I say مثلا gigabit Ethernet, which means I need to have an output speed on a particular port 10 gigabits per second. This means that the service rate inside the router should be 10 gigabits times the number of input ports. Okay? Which represents the worst case scenario. So that's a goal that's usually maintained inside the router if we were to say that this router supports 10 gigabit Ethernet مثلا, or 10 gigabits per second on any output port. In order to maintain this 10 gigabit per second, I need to have a service rate which allows me to process the packets on all the inputs ports with a speed that allows me to exit that rate. Okay? And the switching fabric should be extremely fast to switch all the packets coming from the input ports to that particular output port with a very, very high speed. Okay? That's why this goal is not easy to achieve. So, but this is actually controlled by what? This is controlled by the incoming data on all the input ports and also the queuing delay, صح? And the switching that happens inside the switch fabric. So 3 things. What is the rate? The queuing delay here, and the switching speed. Okay? So all of this should maintain a service rate which allows me to have 10 gigabit per second on the output port. ماشي؟ طيب. In order to achieve this goal, we have different architectures for the switch fabric. The switch fabric itself has different architecture. Now we're getting to architecture. We're getting to computer architecture. So there are 3 categories of switch fabric architectures. So these switch fabrics could have the architecture of a shared memory. Shared memory معناه إيه? If I want to send to a particular output port, I send to a particular address range inside the memory. Then this output port will be connected to take automatically the packet from this memory range, and then it sends it to the output port. That's one architecture. The second architecture is the bus architecture. Bus architecture, as we all know.
No storage.
So no storage. I don't have to store anything, which means that any input port, one input port should have access to the bus at any point of time. So I should allow only one of these input ports to write on the bus. But any of these ports can read at any point of time. So I don't have a problem who will read. I have the problem who will write. So write has to be single access. Read can be anyone. Okay? So that's another architecture which limits also the speed. It's cheap, it's simple, صح, but it has some limitations. Here we call it crossbar, or sometimes we call it Banyan network. So that's another architecture for the switch fabric, which allows now to have crossbar architecture like this, and any of these intersections can be activated at any point of time, so that I could have simultaneously multiple input ports connected to multiple output ports. And then the control system will control which of these intersections will be activated to connect this input port to this output port instantaneously. But here potentially I could have مثلا two writes and two reads happening concurrently. صح؟ بس طبعا the cost of the design for these particular networks is much higher, as you can imagine. So these are all of them, they have to maintain an input switching rate n times the line rate desirable. So if we want to maintain 10 gigabits Ethernet, 10 gigabit per second at the output port, then we have to allow each of these architectures to have n times 10 gigabit per second, okay, in terms of service time in the switch fabric.
Comparing the first with the third vector complexity.
It depends. We'll talk about this. We'll talk about the details of this. So it depends. It depends بقى الميموري نفسها, shared memory, how it's designed. We'll talk about this. So these are the three types of the switch fabric. Getting into each of these ones, the first generation routers, they said the simplest one, we know how to design shared memory. But the problem here is that shared memory is actually single access. Read or write. Okay? That's in the past. Of course, we have more sophisticated memory architectures now, which allows us to have multiple access, to write, multiple writes and multiple reads, which potentially corresponds to the Banyan network, but using the shared memory architecture. Okay? But that only happened recently. But in the past, we used to have this simple memory architecture which only supports one access at a time. Which means that if I want to send from one input port to a particular output port, we first have one access to write to a particular shared area inside the memory where this output port can read from. Okay? And in another time cycle, so if we were to assume that we have a clock, in the first cycle, we write. In the second cycle, this will read. Okay? So in order to send one packet from one input port to one output port, we have to have two memory access cycles. Okay? That's a limitation here. This will limit the speed. And also we have to do only one access at a time. We cannot do multiple access, whether read or write.
Yeah, so one for writing, one for reading.
Yes. Okay? So this is used in this, this is very, very old style routers that uses this type of shared memory architecture. But of course, these speeds so we have two bus crossings per one datagram. We have to write first and then read. Of course, that, as you can imagine, for مثلا 100 megabits per second line speed. So these types of shared memory with single access were actually being used in very old versions of routers, اللي هي Cisco Catalyst 8500. Okay, so the line speed in these types of router was not more than مثلا 100 megabits per second or something like this, which was at that time was high, but now it's very, very slow. طبعا now, alhamdulillah, luckily we have more sophisticated memory architectures that can support multiple concurrent input and output all at the same time. but that requires more sophisticated chip architecture inside the memory. So that's currently, by the way, the shared memory architecture came back as the dominant architecture for designing routers. Recently, once we were able to design this shared memory architecture with multiple access. Because in the past, the shared memory architectures kind of disappeared and lost ground to even the bus architecture and the Banyan network architecture. But then later on came back and it became the predominant because it gives you the highest degrees of freedom in terms of allowing multiple access on the memory. Okay, so you can perform multiple inputs and output concurrently at the same time. So you can write in any location. As long as you are writing to different location, the chip architecture allows you to have these concurrent writes and concurrent reads happening concurrently at the same time. ماشي?
Doctor, how come previously it wasn't the case? Like, how come different ports can't write at the same time?
That's a limitation in the hardware architecture design. Yes, the chip. In the chip design, you cannot do this. In terms of logical gates. Okay, there was a limit. You cannot have multiple writes at the same time. Even if you are writing to different address. This memory architecture supports only one access at a time, regardless of which address you're writing to. But the recent designs, as long as you are writing to different address, you can have concurrent addresses, you can have hundreds of accesses to the memory, as long as you are writing to different address inside the memory.
In this case, when you say address, you mean like the port number itself?
لا, a location, a particular location in the memory, yes. Which is mapped to a particular output port, yes. To a particular output port, yes.
Understood.
Yeah. So the bus here by the datagram from input port memory to output port memory via a shared bus. For the case of the shared bus, as we said, we are limited with one input port having access to the bus at any point of time. But we don't have to care about who will read. Of course, when we put the packet on this bus, we put a label we write to a particular shared memory. We put a label with the packet, okay, that will refer to which output port should read this. So here the technique is slightly different. In the memory, we don't have to add this label. We can write to a particular memory address which is allocated to this particular output port. But here, with the packet, to write it on the bus, we have to put a label. And also we have to control only one input port having access to the bus at any point of time. Okay? But we don't have restriction that the writes and the read can happen in 2 clock cycles. No. Once we write, anyone can read. There's no issue. All of them will read. The one that will pick it is the one that has the address or the identifier matches the label in the packet. Okay? So in the past, with the limitation that we had in the shared memory, the bus architecture can provide faster line speed. And it's simple. So it was attractive at that time. But that's because of the limitation in the memory architecture. Okay? So once we redesign the memory architecture to allow multiple writes and multiple reads, of course, خلاص, the shared memory architecture dominated the speed. Okay? Which potentially responds to this shared architecture. This shared architecture overcome the bus bandwidth. طبعا الباث bandwidth, only one input port can write to the bus at any point of time. Okay, so we have a limitation here. So potentially we could have n packets on all the n input ports, but we allow one at a time. So we have to go one by one. Okay, that's a limitation. So to overcome this bandwidth limitation, we can use the Banyan network. The Banyan network now, it uses the bus architecture, but in a more sophisticated way. So we have multiple buses that are interconnected. okay? And by activating a particular intersection points, we can potentially allow مثلا this port can write to this port, and this port can write to this port, happening both in the same cycle. مفهوم كده؟ مفهومة دي؟ By controlling بس the intersection points. And we can do that in hardware. We can control this, and in that case we can have potentially higher line speed. ماشي كده؟ So we can have advanced design. Yeah, one of the issues here, in order to really maintain very high speed, as you can imagine, if we have the packets having the same size, we can maximize the speed of switching here. Okay? Because if you have long packet going this way and very small packet going this way, you have to wait for the longest size packet, huh? Okay? Which will delay the smaller one, huh? So the smaller one can actually go fast, but it has to wait for the long one. Okay? So in order to optimize the line speed, they also try to restrict the size. How can they restrict the size? Using the concept of fragmentation. We'll talk about fragmentation again in the second half of the... But fragmentation here happens inside the router. Okay? This is happening inside the router. So if you have a packet like this, you divide it into two equally sized cells. Okay? And then they take one cell, they send it using this concurrent access, and then here in the output port, they reassemble the cells into one packet, and then they send it. So by doing this, they increase the speed, but they pay the cost of fragmentation and reassembly. So it's a trade-off. But usually these types of switch fabric architectures, they use that concept of fragmentation and reassembly. Fragmentation and reassembly is a concept that's used in different levels, and we'll talk about it again when we talk about IP. And that's used in this particular output for 60 gigabit per second. So as you can imagine, here the speed is much higher, can support much higher speeds. But in fact, nowadays, we can achieve even faster than this using the shared memory architecture, but with a multiple access. Okay? Anything not clear?
We are describing the complexity, but it's not really the real complexity in such architecture, because, like for example, in each arrow here, there is one direction, but basically it's four tuples. So each one
Yes.
is input and output.
Each صح مظبوط.
So this makes it much more complex than...
Of course, you're perfectly right. So يعني here the architecture is much more sophisticated than this, because each input port is in fact an output port.
Yes, exactly.
So you can write and read at the same time on the same port.
Even in such architecture. So
Yes, of course. Yes.
In the same,
Yes.
direction.
طبعا. Yes. طيب الاوتبوت بورت بقى of course it has برضه queuing. هتقول لي طب output queuing ليه؟ خلاص the packet has been switched. So in the input port we have to queue things because the switching fabric has a limited speed, صح؟ But here خلاص we exit. Why do we have to store again the packet at the output port? Okay, again for one reason, the speed of exiting the packets from the switch fabric to here again does not match how it's being used on the next network. For one reason, مثلا, this could be the output port could be a wireless network. Okay, for wireless network we do what? For wireless network, الناس اللي خدت network 1 و network 2. For wireless, what do? Can we send anything over wireless without checking anything? ايه اللي هيحصل؟ Collision, صح؟ We go into collision, صح? So what do? We use a carrier sense multiple access. So we have to wait until the channel is free before we can send. Wait معناها ايه؟ Okay, wait معناها we have to wait for your turn So it's exactly similar to, again, coming into a bank and the service rate is not defined, so we have to queue in the line until the teller is free, right? So that's one reason why we have to stay even at the output port. So that's why we need a queue at the output port, okay? Another reason for this is in fact the scheduling discipline. Scheduling discipline here refers to the fact that احنا قلنا IP is not virtual circuit, صح؟ بس احنا we mentioned the fact that we could have some priority for these packets. We could have some priority for these packets. So packets that are coming, يعني مثلا, can you imagine that the traffic belongs to Ooredoo sending traffic to China has the same priority like Amr مثلا sending some packets to China? Of course the priority is different. Ooredoo will be higher priority, صح? Will be prioritized higher, صح? So we have
They check that flag that you mentioned.
so in IP, and again we'll talk about it today again, we have, remember when we talked about the IP header containing explicit congestion notifications, huh? We talked about this when we talked about congestion, but we said this part is not used because we don't do explicit notification from the network, because after they designed explicit congestion notification, they found that this is not scalable. We cannot do this. Okay, but here there is another part which is very important. In network one, of course, which nobody remembers, but in network one also we talked about another field here called another field called اللي هو السي اللي هو DS CP. فاكر حاجه زي كده؟ differentiated service code point. Basically it's a priority. Okay, the packet should have priority, which means that of course traffic belonging to مثلا multimedia traffic, okay, should not have the same delay like network or web browsing. صح? So multimedia traffic should go very fast. Should have some delay guarantees. But you told us that there is no delay guarantees. This only happens in virtual circuit. صح? We said that here we don't provide delay guarantees per virtual circuit. We don't have to do this, but we provide it per class of applications. Okay, so IP is still best effort, but we may actually also provide some priority for the packets, which allows us here in the output port to schedule when this packet should go on the output line depending on its priority. So IP provides at least the ability to have priority in the packet, but it does not say how you should implement that. It's up to you. تفضلي.
based on the application.
صح.
احنا عندنا اصلا layer.
صح.
How to explain this?
هو the application doesn't have to establish a virtual circuit end to end. All it needs is just to say, okay, these packets are important. So please, if you have a room, try to schedule these packets fast. Okay? Without establishing a virtual circuit. But maybe after all of this, the packet gets lost aslan, not delivered fast. It doesn't get delivered aslan. Okay? So still IP is best effort. Okay? But it will try, ما هو best effort معناها ايه؟ I will have to do my best. Okay? طيب, assuming that my best allows me to have some differentiation between high priority packets and low priority packets, I can do that. طب how do we do this? Sometimes the queuing is a little bit complicated. So So we have multiple queues depending on the priority. So based on the incoming packet, we read this DSCP. We say, this is priority 10. So we put it in this queue. This is priority 9. We put it in this queue. And there is a scheduler. That's what's referred to here. The scheduler will say, okay, do I have any packet in the highest priority? If yes, then I will have to let this go the first. يعني اللي هو ايه عنصرية بقى. يعني I have مثلا ايه 10 queues in the coming to the bank. Okay? So these are VIPs, these are VVIPs, these are normal people. Okay? هي كده. Now differentiated services refers to differentiation. But هنا الدiscrimination هنا in good sense, not in bad sense. Discrimination in good sense. معناها packets with high priority should go first. Why? Because I want to try to meet the expectation of the customer because he's paying a lot of money. Ooredoo has very sophisticated service level agreement with AT&T. Okay, I have traffic coming from Amr, traffic coming from Ooredoo. لا, traffic from Ooredoo goes first because they pay a lot of money. Amr ده ما بيدفعش حاجة. See, here it's normal. It's understandable. يعني. Again, IP does not say how you should deal with this priority. Okay? But at least it provides the way to store the priority of the packet in the IP header. We'll talk about this. But it doesn't say how to deal with it. So some routers might implement this sophisticated queuing disciplines. Some routers might say, okay, so I will not do this. هو one queue, everybody goes, it's democratic يعني way, and all people are equal. خلاص. Okay? But of course, these types of routers will not provide high satisfaction to high priority users. Because it deals with all the traffic equally. Okay? So this is what we refer to. And I'm saying all of this because of this scheduling discipline. Otherwise, I would not have to talk about all these details. But in case you read this, you understand where this is coming from. Scheduling, على فكرة, is one of the hottest areas of research in the core network. Scheduling. There is huge amount of optimization that goes into here. Okay? طيب, let's just break عشان الناس ما طيب, okay. Continuing the discussion. طبعا we talked about this this example where we have, on the worst case, many input ports are trying to send packets to the same output port, in which case we have some kind of contention, right, on this output port. That could lead to some delays because eventually we have to write one packet at a time to the output port. But these packets, they will line up in the queue at the output port. So you could have also a buffer overflow at the output port. Okay? So in case of buffer flow, after you do all the switching, you find that there is no place in the buffer at the output port, so you have to drop the packet. So concurrent access to the same port could lead to a delays or packet loss. طيب. So that leads to another question. So given this situation, and if we want to maintain a certain speed at the output port, okay, what is the ideal buffer size of that queue?
Equal to the maximum that can take as an input.
Yeah, but what is that in terms of the input, the incoming traffic, and the likelihood of having multiple input ports writing to the same output port? Okay. So some experimental studies, specifically this RFC, we don't have to طبعا يعني memorize numbers, we don't care about this, but it actually came with the conclusion that the average buffering in terms of size is equal to the round trip time. And we know the round trip time, طبعا, as we all know, the round trip time varies over time, صح? Okay, so we can have a worst case. Okay, so let's say مثلا 250 milliseconds times the capacity or the actual rate that we want at the output port. Okay, this round trip represents what? It represents the time from the time you send the packet until you get the response. Okay, so you calculate this. طبعا we calculate the worst case scenario, and then we multiply this by the capacity that we want on the line. And the buffer size, again, this is experimental. This is like heuristic. It's not by any means an ideal or optimal or something like this. But this experimental study came with actually two different estimations. One says that it has nothing to do with the number of input ports, and it's simply round trip time times the capacity. Another study, recent recommendation, it says that it has to do with the number of flows. So it's actually the round trip time multiplied by the capacity divided by the square root of n. Nobody asked me where that came from. This is an experimental study. Again, it has nothing to do with math calculations. This is based on empirical experiments. It's not in any way something mathematical that leads to an exact calculation. No, it's some empirical experiments that came up with this recommendation. We don't have to really memorize this or know where this came from, but we take these as guidelines. So we usually calculate the size of the buffer using this formula or this formula, and then we can increase or decrease depending on the design factors that we take into consideration. ماشي? The more important thing here is another phenomena which we call it head-of-line blocking. This head-of-line blocking is a phenomenon that comes up with any queuing system. That's a very interesting phenomena that happens because of this concurrent writes of multiple input ports trying to write to the same output port. So the idea here is that imagine that we have a switch fabric which tries to switch packets, and the color of these packets refer to where this packet is going to. So red packets will go to this output queue, blue packets will go to this output queue, and green packets will go to this output queue. Okay? So if we were to have this scenario where we have packets lining up on the different input queues, and we want to switch these queues to the particular output ports depending on the color. Okay? So as we can see here, that because of the fact that this packet should go here and this packet should also go here, okay, the switch fabric cannot switch both at the same time to this particular output port. Okay? They have to have different clock cycles, the least, صح? So we have to have, if we decide to write this one, then we have this one has to wait. Okay? So the scenario here, this is the next step. So this packet goes to here, but this packet has to wait for at least one clock cycle. But there is an interesting thing that happens here. See, because of the fact that this one has to wait, everyone behind it was blocked. Even the fact that this green one should go here, which is different from this red output port. So it would have been good that the switch fabric would say, no, let me write this one first.
Because the green is empty.
Yes, but then this one will also be blocked. So in all cases, you have the phenomena that we refer to as head-of-line blocking. Okay? That's exactly similar to the banking scenario that we've been talking about. So you have multiple lineups, okay? Multiple lineups correspond to the different doors of the bank. Each lineup lines up in front of that input door. one from this queue should go to the teller, one from this queue should go to the customer service, and so on and so forth. So if you have the head of line here, the head of line here, they want to both go to the teller, for example. Okay? So one will go to the teller and the other one will have to wait. Waiting here معناها he or she will block all the ones behind them. You see that? That's regardless of whatever switch architecture we talked about so far. Yani regardless of whatever switch architecture you have here, this head of line blocking is a phenomenon that happens and it causes some limitation in the speed. So we just need to understand this head of line blocking because it happens very frequently in the router and it kind of limits because of this is caused by the fact that the queuing system is always first come, first serve. It's not a heap. Huh? It's not a heap. It's a queue. Queue معناها ايه؟ First in, first out. ماشي؟ If it's a heap, then it's a different story. ماشي؟ واضحة دي كده؟ So this is the phenomena of line blocking. So now we will cover this part as we know that in the network layer we have the most important one is IP. So now we need to discuss each of these protocols briefly. Okay, this one will take the longest part. So we need to discuss IP, we need to discuss ICMP, and then we need to discuss the routing. The routing protocols, we will not discuss routing protocols. We'll discuss routing techniques. Routing protocols, we assume that we have studied that in Network 2, but here we'll focus on the algorithms. Okay? So first we'll talk about IP. IP protocol, again, in terms of protocol data unit structure. What is the header format of IP? Again, we'll cover that. This is a review from Network 1. All these protocols, they exist in the network layer. We call them the network layer protocol suite. A protocol suite refers to group of protocols that work hand in hand, okay, to perform a particular network function in a layer. Okay? So these protocols are interrelated. They have to work together hand in hand. ماشي? They are kind of isolated from the transport layer. صح? TCP is kind of isolated. But this network layer, they have to work hand in hand. IP, we know IP is best effort and it's used for packet forwarding. Okay? We have ICMP where it's used for error reporting and troubleshooting, where we have to do ping, trace route, things like that in order to, we use these commands for troubleshooting so that we know when we send a packet, if we send a packet to China, okay, how does it go to China? We want to trace the packet, how it goes to China. Okay, so we want to see all the routers, the routers it goes through. Why? Because this packet seems to be blocked at some point, so we want to know which router has the problem. Is it the router in Qatar? Is it the router in Abu Dhabi? Is it the router? So we do trace route, so we know which router has the problem. So we do this as part of troubleshooting. So that's where we use ICMP. Okay? And of course, routing protocol, we use it for planning, as we said, for planning the route end-to-end. So this is for packet forwarding, troubleshooting, and planning the route end-to-end. Okay? So we go through each one. So first, the internet protocol, as we said, this is the predominant protocol in the internet. One thing interesting we notice here, talking about the IP header, it gives you some indication about how imperfect the protocol designers are. They are human beings. So we will see here that many of these fields, we're talking about IP, the most important and the most common protocol used on the internet. When we talk about this header format, you see that many of these header fields, they are not being used. Can you imagine that? First of all, version. So first of all, the header format is kind of structured as 4-byte words. So 32 bits, 4-byte word, 4-byte word, 4-byte. They are structured as rows. Each row is 4 byte words. Okay? Each row you have one or more fields. Each field indicates something. Okay? So the version, first thing, the version. Why do we need to have the version? Is it version 4 or version 6? The version here is important so that you know if you're talking the same version, then you can negotiate. You can have conversation. If we're talking different versions, then our conversation cannot go through smoothly, which means that we talk different language, right? But version 4 here, you will see on the internet, it's 99.9%. It has 4, number 4, which is IP, version 4, which means that this field will always have 0100. That's it. 4 bits, 0100. 4 refers to 4. Okay? They have this why? Because you may have مثلا a protocol which is 4.1, 4.2, and you have different versions of version 4. But then when they talked about a different version, they found that they have to come up with a whole new protocol, version 6. And in that case, the whole header structure has changed completely. So this version is actually it's not very significant. Okay? Because for version 6, the whole header structure changed completely. Header length. We have the header length. You have the length here. Whenever the header, it refers to the length of the header, صح? We refer to the length of something when the size of this changes, صح? When it's variable. Okay?
We will have the same size.
We always have the same size. It's actually 20 bytes. But in the design phase of IP, they refer to this options field. This options field should contain some information about timestamp and record route and some other meta information which should be used with IP, but then they realize that none of this is being used. Which means that this options field is always 0, which means that the header length is always 20 bytes. Is always 20 bytes, which means that you always have 5 rows here. Okay? So if you have 5 rows and it's always 20 bytes, why do you have to have header length? If the header length is fixed, why do we have to have the header length? Okay? Another thing here you have to pay attention to is that this header length is actually, it's again 4 bits. So in the standard, they say that the header length ranges from 20 bytes to 60 bytes.
Maximum 4 bits are enough.
How
4
come?
bits are more.
Yeah, not more. What is the maximum number we can represent? We can represent using 4 bits.
32.
32. 2 to the 4 is.
2 to the power 4, which is
Okay, 16. So it is
actually the maximum size is 15. 4 ones is actually 15 because we start from 0.
Yeah.
So the maximum size is 15. How can we have 15 refer to 60? Okay? Okay? It's simple. So the number here refers to the number of rows, which means that each one refers to 4 byte words. Okay? So 15 times 4 bytes is 60. Okay? But this, in fact, is always 5, which refers to 20. So it's actually 01, معلش هو القلم بطل يكتب 0101. It's always like this. Why do we need to have a field that will always have the same? It's redundant, okay? Because this option field is never used. It's actually never used, okay? This length is the length of the header plus data. This is very important. Okay, so this data field can contain by variable size data, which can range from 0 all the way to 1500, 1600 bytes.
that one is useful.
Yeah, this one is useful. We have to maintain it, so there's no way around it. Even IP version 6 has payload length. ماشي كده؟ طيب 16-bit identifier. 16-bit identifier refers to identifier for the packet. when did we need it's similar to the sequence number in TCP, صح? صح? Identifier, it identifies the packet, صح? It's similar to the sequence number in TCP. Is it? When did we need to have sequence number in TCP? Why do we have to have sequence number in TCP?
To know the loss of acknowledgements.
To know the order of the packets.
The order. That happens when we need to have reliable transmission. صح؟ أيوة شفت بقى this is the thought process I want you to go through. Okay? We don't need to have ordering here. IP is best effort. It never claimed it maintains any kind of reliability. So in fact, this identifier is used for totally something else. It's not used for providing reliability whatsoever. This one, together with the flags and the fragment offset, are used for a totally different process. It's called fragmentation and reassembly. Okay? We'll talk about this in the next slide. So in IP, we need to do fragmentation and reassembly. Okay? For now, you need to understand that fragmentation is needed. Why? Because we always deal with different technologies in the next hub. So from one router to another, we may use wireless. For the next one, we may use optical. For the next one, we may use satellites. For the next one, we may use Ethernet. Okay? From one technology to another, there is a maximum transmission size unit that you can have on any technology. Okay? So for example, from Ethernet to wireless, we need to drop the packet size from 1500 to 500. But how do we do this? We have to use a fragmentation. So we divide the 1500 into 3 units. This is called fragmentation. And then we do defragmentation, اللي هو reassembly. So we have to do this. Okay? So we use identifier with the flag and the fragment offset. Those 3 are used for a fragmentation and reassembly. Time to live, another thing which has discrepancy. What is the function of this time to live? It's 1 byte. Huh?
It decreases by the moment.
Okay. It refers to in the standard as the time that the packet should last inside the network. But is it actually a time? It's number of hops. So the name is misleading, actually. The name is misleading. It doesn't refer to the time. It refers to the number of hops. So when it starts the packet, it should have here number of hops equal to 255. When it goes to the first router, it gets decremented. So it becomes 254. And so why do we need to do this, huh?
So the packet doesn't route in the...
Yes, to avoid a packet looping, right? Otherwise, we would have packets that's still in the internet until today, that gets sent in early century. Can you imagine this? Of course not. So the packet will have to go into different routers, and then at some point, the router, even if it has buffer and everything, it checks this field. If it's 0, then it drops it. This means that the packet has been looping in the network, and it's not going anywhere. But in fact, it's not a time. It's not a time. So the name is very misleading. It's not the time to live. It should be called a hops. Number of hops. Okay. So that's why in IP version 6, if you look at the standard, you will see that this is called hop count. It's IP version 6 is built on the lessons learned from IP. You will see the header is very clean. The header length is fixed. No header length aslan. Okay? This is called hop count. Everything is like logical. Why? Because they learned so many lessons from IP. There are so many imperfections in the design of IP, although it's the predominant protocol on the internet. Okay?
You took to send a packet from one side to the other side. You need less than this number.
Of course, yes. Yes. You need less than 255 for sure. Okay? Yani there is also one reason for this, which we will talk about at the end of this chapter. Okay? Upper layer. This header, this field is also important. Why? Because remember, IP should eventually send a packet to the upper layer, صح? Okay. So send it where? Does it have to send it to which protocol in the upper layer? Remember, all these protocols, they run as software processes in the higher layers, with the only exception of the physical layer, because it's purely hardware. Okay? But from the physical layer to the data link layer, it has to be sent to a layer of hardware. But once we switch to software, the protocols run as software as processes. صح? So should I send it to the UDP process or the TCP process or ICMP process or CTCP process or what? So I have multiple processes. So this upper layer protocol should have a specific number to refer to TCP, specific number UDP, specific number ICMP, lower the protocol that we talked about in the previous slide for troubleshooting. Okay? So this protocol, you will see that it always exists starting from the data link layer above. In the data link layer, if you look at the standard, you'll see upper layer protocol. Okay? In IP, it refers to TCP. What about TCP? TCP has to send it to a particular application. Through what? Huh? Through the port number. Yes, to a particular socket, given the port number. Yes. So this has to be maintained in all layers. This is very important. Okay? So that's why we need to have this upper layer protocol to refer to where should I put this protocol data unit to the next layer. Header checksum. Header checksum refers to إيه بقى؟ بالضبط. برافو عليك. Even this was removed in IPv6. Why? Why? Because they found something very interesting. Here, IP is used in the core network. Core network, usually, or 90% of the time, it uses wired. And it uses very reliable network topology. The probability of packet loss here in the core network is very small. And even if it happens, it has a probability of 10 to the power maybe minus 19 or something like this. So the probability is very high. But I actually have to maintain 16 bits for that in every single packet sent over the internet. Okay? So when you weigh the gain, it's almost useless because the probability of packet error or packet corruption in the core network is very small. If you talk about it for TCP, I can understand because it's end-to-end. But here in the core network, the probability is very small. That's one of the reasons that in IPv6 was removed. Again, it's built on the lessons learned. This is the source IP address, destination IP address, which is 32 bits. Of course, as we said, there is a limit for the number of addresses, 32 bits, and that's why in IPv6, again, based on lessons learned, they made it 128 bits. Why? Because again, there is an explosion of hosts and devices on the internet. Okay, so if we make this 128 bits and leave all these complexities unnecessarily, then we did not learn anything. So they tried to mitigate or compromise. Okay, so we will increase the number of bits allocated to the address, but we have to simplify all these fields that are not used. So they removed version, they removed header length, they removed all the fragmentation and reassembly fields. All of these are removed. Checksum is removed. Okay, so the header is much more simplified. Much more simplified in IPv6. In fact, they added back some meaningful things, like some fields that has to do with security. It's providing security guarantees in IPv6. Okay? So they cleaned lots of things. And also, of course, these options removed. This is the first thing. They removed this. It's never used. And it creates some complexity in the header unnecessarily. تمام كده? Okay? So typically you would have the whole protocol data unit. It has 20 bytes TCP header and 20 bytes IP header. So 40 bytes IP header plus TCP header, or TCP header first and then IP, and then the rest of the application data. Any question?
So for version 6, they freed up to like 200 bits from this. Just to
I don't know. You count it. Okay. يعني لا, many fields have been removed. So if you look at IP version 6, although you might think that IP version 6 is very complicated, but when you look at the header structure, you'll see it's very clean and very simple to understand. So it comes from the lessons learned from IP version 4 in many ways. We will explain conceptually, how the fragmentation and reassembly works, and then we will continue next time, inshallah. So IP fragmentation and reassembly, as we said, we need to account for, from in the core network, from one hub to another, we might go through different technology in the lower layer. What is the implication of this? In every technology, whether it's Ethernet, fiber optics, wireless, satellite, things like that, there's only one thing that we need to care about here. What is the maximum transmission unit here? The maximum transmission unit size that we can support on this technology. Okay? So that limits the size of the packet size that we need to send over the next hub. So assume that we have here Ethernet, which is 1500 bytes. And this is wireless. Wireless has a limit of 500 bytes. What do? We have to fragment these 1500 bytes into 3 fragments. Okay? That makes sense. But the important question now, what do we do here? So if we go here and then we find that the maximum transmission unit here is 500, then we don't have to do anything. Type. What about if it's 200?
Again, we do fragmentation.
We do fragmentation again. So fragmentation can be recursively done many times from the beginning to end. Type. What about if the size here is 2000 بقى?
We do reassembly.
غلط. That's what we don't do.
We don't do.
Why? اللي هجاوب دي بقى يبقى
Why should I?
ايه؟
Why should I?
Why not?
Because
I would
it
be
might,
wasting my
Why
time.
not?
the size is difference. The size
Eh?
difference between the packets.
Yeah.
From wireless and
Yeah.
from.
Yeah.
I will reassemble.
The size doesn't differ. No. If I send packets of size 500 on a line that supports maximum transmission unit of 2000, then I'm fine.
It's just I don't waste too much time reassembling them.
Why? Because of 2 reasons.
Quality of service, let's say.
No, not
I
necessarily.
have to know which 2 packets to reassemble.
No. Eh?
I have to know which 2 to reassemble and this with packet processing.
You're getting into the right direction. صح. One reason is that what if I have here, if I do reassembly here, then I end up here with again 500. Then I have to do
Yes.
reassembly and then do fragmentation again. صح? That's one reason, but that's not the strong reason. The strongest reason here is that when you fragment, this packet becomes 3 independent fragments. Each fragment is an independent IP packet. Independent. What does that mean? This means that this independent IP packet may, in fact, get sent through different routes. Because IP never guarantees the same route for the packet. It never says that.
They only look at the destination.
They only look at the destination number. أنت حظك يعني. I can send it here, I can send it here, I can send it here. There's no guarantee. I don't guarantee anything.
So to guarantee the order of arrivals of the
إمتى? Where?
the receipt.
At the final destination, not at the router خالص. I didn't say that. صح? So they can arrive to the different routers in different orders, and this is completely fine. They can take different routes, and this is completely fine. Okay? So what I will try to do is that I will deliver to the final destination, hopefully in the same final destination, not to another destination. That's the only thing I can do my best to do. Again, I can fail to do this. And it's bardo, I cannot do anything about it. Right? So if I cannot, I never do reassembly in the core network for these two reasons. Because I don't have to reassemble and then fragment again, reassemble and fragment again. I can do multiple fragmentations, but I never do reassembly in the core network. Where do I do the reassembly? Where? In the final destination only. مش clear?
Why do I even think about reassembling?
Why not? يعني why not? يعني you have to ask yourself this question يعني. Why not reassemble in the intermediate routers?
Should be constant reassembly and fragmentation at each hop, no?
Why do you
Each
think-
route.
لا بس بقول لك اهو, this is the strongest reason why we can never do reassembly in the corner. We can never do reassembly in the corner. Why? Because each fragment becomes an independent IP packet that might take different routes.
Yeah, but taking a
So if you wait in a specific router for all the fragments to come to do the reassembly, you might wait forever.
so latency is the issue.
لا, not latency.
But it's not
You
even-
cannot do that. You cannot do that. It's not feasible.
Okay.
It's not feasible. خالص. You never do this. You do it only one time at the very end, at the destination. But you can do multiple fragments, and that you have to do this. You have to be able to do this because you might go from wireless to مثلا Bluetooth. So you drop from 500 to 200. What do?
Right.
You have to fragment. So you can fragment multiple times. When you fragment and fragment, each of these fragments become an independent IP packet with full header
Right.
and full payload.
So that's there is no.
So the main header fields that change are the length, صح?
Yeah.
And what?
See,
And the three headers that we talked about, the identifier, the flags, the fragment offset. All these four fields, they will change for every independent fragment. And each fragment becomes an independent IP packet that may take different routes. They might arrive out of order. They might not arrive أصلا. All these scenarios are possible. ماشي? So the rule is we never do reassembly in the core network. We never do this. We do reassembly once at the very destination. But we can apply multiple levels of fragmentation. We can always do this.
uh,
اتفضل.
how do we organize the fragmentation and they call it the identifier?
ما هو ده بقى this is what we will الحلقة الجاية بقى this is what we this is what we will answer next lecture or we can talk about it this lecture بس بتهيألي يعني we have to do some calculations and some stuff like this so let's move it to the next lecture إن شاء الله. Okay? Any other questions? تمام كده? Okay, let's break and go to the presentation. Who's doing the presentation today? Okay.